In the year 1673, the French physicist Edmond Marriott gave a paper to the Paris Academy of Science which contained experimental data proving for the first time that the force on an object moving through the air varied as the square of the velocity of the object. That is not necessarily intuitive. You double the velocity, a lot of people would think you double the force on the object. This says you double the speed, you quadruple the force on the object. And Marriott proved that the force varied as the square of the velocity of the object. Prior to this time, as I said, conventional wisdom adopted that idea that the force varied directly with the velocity. After Marriott's finding, the velocity squared law for aerodynamic force became widely accepted. Then, in the early 18th century, the English ballistics expert Benjamin Robbins, while experimentally measuring the aerodynamic drag on artillery projectiles, observed for the first time that when the projectiles were moving through the air at speeds near the speed of sound, the aerodynamic force, in other words, the drag in this case, began to vary as the velocity cubed, not velocity squared, as in the lower speed case. This is the first time in history that what today we call the transonic drag rise was observed. And in 1742, he presented his findings to the Royal Society. We know today that the cause of this large drag increase was shock waves. Now, in 1870, William John Rankine, a noted engineering professor at the University of Glasgow, correctly derived the proper equations for the flow across a normal shock wave. Not cognizant of Rankine's work, the French ballistician Pierre Hugonot rediscovered the normal shock wave equations in 1887. To the present day, the governing equations for flow across a shock wave are called the Rankine-Hugonot equations in honor of these two men. In 1887, the Austrian physicist Ernst Mach took a photograph of the flow over a supersonic projectile, in this case a .22 caliber bullet, as it streaked down a range in his laboratory. By means of a special optical system, Mach was able to photograph a shock wave emanating from the nose of the projectile. This is the first time that a shock wave was ever seen by human beings, proving that indeed shock waves do exist. By the beginning of the 20th century, the large drag increase on projectiles as their velocity passed through the speed of sound was well known. For example, ballistics measurements on projectiles carried out by Bensberg and Kranz in Germany in 1910 yielded the variation of drag coefficient with velocity for the transonic and supersonic regimes. The curve shows a large rise in drag coefficient near Mach 1 and the gradual decrease in the drag coefficient in the supersonic region. By the way, that doesn't mean that the drag goes down, it's the drag coefficient that's going down. Keep that in mind. At the end of World War I, the top speed of high-performance fighters, such as the SPAD-13, was only about 130 miles an hour, nowhere close to the speed of sound. Yet in 1918, engineers at the U.S. Army Air Service Engineering Division, McCook Field in Dayton, Ohio, built a wind tunnel capable of producing a test stream with a stunning velocity of 465 miles per hour. Now, why? Were they looking ahead to airplanes flying at 400 miles an hour during World War II? Not really. The velocities encountered at the tips of propellers of World War I airplanes were so large that when combined with the forward speed of the airplane, the propeller tip speeds could be close and even exceed the speed of sound. When this happened, the propeller efficiency suddenly decreased. What was causing this sudden decrease in propeller performance? What was happening? They didn't know. To find out, Frank Caldwell and Elisha Fales, two engineers of the propeller division, constructed the high-speed wind tunnel at McCook Field to test the lift characteristics, not drag, the lift characteristics of airfoils at speeds near the speed of sound. This is the first time that high-speed effects on lift had ever been observed. And they discovered that beyond a certain speed, what they called the critical speed of 350 miles an hour, that the lift decreases so much on this airfoil that it essentially drops off the cliff. Since the thrust of a propeller comes from the aerodynamic lift produced on the propeller blade, twisted so that this lift is in the forward direction, when the lift fell off the cliff, the thrust suddenly went to pot, and the propeller efficiency degraded towards zero. So in 1918, it was suddenly discovered that the loss in propeller efficiency at high speed was due to a sudden loss of lift at in a region or near the propeller tip. But nobody had a clue what was causing this sudden loss of lift. They discovered that beyond a certain speed, what they called the critical speed, in this case, for their case, was 350 miles an hour, that the lift decreases so much that it essentially drops off the cliff. Since the thrust of a propeller, comes from the aerodynamic lift produced by the propeller blade, twisted so that this lift is in the forward direction. When the lift fell off the cliff, the thrust suddenly went to pot, and the propeller efficiency degraded towards zero. So in 1918, it was suddenly discovered that the loss in propeller efficiency at high speed was due to a sudden loss of lift in a region near the tip of the propeller. But nobody had a clue what was causing this sudden loss of lift. Next, a breakthrough of sorts was obtained by Hugh Dryden and Lyman Briggs in a second series of experiments carried out at the U.S. Army's Edgewood Arsenal in Maryland, where they constructed another high-speed wind tunnel, much smaller, with an airstream only 2 inches in diameter. By careful design of the small airfoil models, 2 pressure taps could be placed in each model. 7 identical models were used, all with different locations of the pressure taps. 13 pressure tap locations were employed. With that technique, the National Bureau of Standard researchers, Briggs and Dryden, measured the pressure distribution now, over the surface of the airfoil at Mach numbers from 0.5 to 1.08. The results were dramatic. Beyond the critical speed, the pressure distribution over the top of the airfoil exhibited a sudden pressure jump at about 1/3 to 1/2 the distance from the leading edge, followed by a rather long plateau towards the trailing edge. Now, such a pressure plateau was familiar. It was similar to that over the top surface of an airfoil in a low-speed flow when the airfoil stalls at high angles of attack. And it was well known at that time that airfoil stall was caused by separation of the flow off the top surface of the airfoil. Briggs and Dryden concluded that the adverse effects of compressibility were caused by flow separation over the top surface, even though the airfoil was at low, even zero angles of attack. To substantiate that, they conducted oil flow tests. An oil with pigment added to make it visible was painted on the model surface. And when the model was placed in the high-speed airstream, the telltale line of flow separation was seen in the oil pattern. Clearly, beyond the critical speed, flow separation was occurring on the top surface of the airfoil. The flow separation was creating the bad compressibility effects, the large loss in lift, and the corresponding large increase in drag. But what was causing the flow to separate? The answer to that final question was 8 years in the future. In the meantime, airplanes in the 1930s started flying faster and faster. For example, on September 13th, 1931, a beautiful, highly streamlined Supermarine S-6B, shown below, flashed through the clear early afternoon sky at Calshot near Portsmouth along the English coast. This exquisite racing airplane averaged a speed of 340.1 miles per hour around a long 7-lap course, winning the coveted Schneider Trophy permanently for Britain. Later that month, on September 29th, the airplane set the world speed record of 401.5 miles per hour. Suddenly, the aeronautical engineer's concern over the compressibility on the propeller tips, an important but tolerable situation, became an absolutely major concern over the compressibility effects on the overall airplane, a problem of showstopper proportions. And by the way, we should note that the design of the Supermarine S-6B was made by R.J. Mitchell, the same person later on who went to design the iconic Spitfire that performed so gallantly during the Battle of Britain in World War II. Now, in 1934, John Stack followed his supervisor's advice to use an optical device, a Schlieren system, to examine the nature of the airflow over airfoils beyond the critical speed. With this system, Stack observed for the first time shock waves occurring above and below the airfoil surface. That was really important. The shock waves are visible, propagating above and below the airfoil about 60% of the chord distance from the leading edge. This is the first time in the history of aerodynamics that shock waves were observed on airfoils. The shock waves interacting with the boundary layer on the surface separate the boundary layer, thus creating the separated flow observed in the 1920s by Briggs and Dryden. This was the final breakthrough in the intellectual understanding of the source of the adverse compressibility effects on airfoils. The intellectual understanding of the compressibility problem that began with the work of Caldwell and Fales at McCook Field in 1918 culminated with John Stack's pioneering Schlieren photo in 1934, showing for the first time shock waves on an airfoil.